Today's video, I'm just going to be looking at the question that we went through in class, and this was based on your IR spectroscopy. Alright, so just to recap, during our covering of your IR spectroscopy, we're looking at your spectrograph, which we're showing the different wave number associated with your specific functional groups. So we looked at a few common examples, and these were your alcohol, your carboxylic acids, your aldehydes, and your ketones. For your alcohol, your R group is going to represent your carbon bonded to another hydrogen, or whatever alkyl chain you're going to have, and there's going to be a hydrogen, a OH group present for your alcohol. For your carboxylic acid, again, you're going to have that R group, and then you're going to have a carbon double bonded to an oxygen, and that is also attached to an OH group. Okay, so we're going to start off with your alcohol and your carboxylic acid. So both your alcohol and your carboxylic acid both have an OH group. For this first IR spectrum represents your ethanol, and that is an example of your alcohol. And this one down at the bottom here represents a carboxylic acid. There are two things to note. In your alcohol group, you have an OH group, a OH only. In your carboxylic acid, you have a carbonyl group, or your C double bond to oxygen, and then you also have an OH group. So in your carboxylic acid, this region here represents your OH group. So your OH peak is typically more broad in your carboxylic acids than in your alcohol. And this region here represents your OH within your alcohol. So if you were to find the wave number associated with this peak, you would match your peak region to your wave number on your IR spectrum. And then you would do the same for your OH group in your carboxylic acid. And because it's very broad, sometimes you may get a bit of a range when it comes to your OH group of your carboxylic acid. This region here is typically your carbon to hydrogen functional group peak. So here we looked at the OH group in your alcohol and compared it to the OH group in your carboxylic acid. So if you were to look at different IR spectrums that were not labeled, you could assume off the bat that, hi, this is an alcohol because it has this particular OH peak, and then you would further confirm that by looking at your wave number associated with your peak. If you see an IR spectrum that's similar to this, you'd be like, that is possibly a carboxylic acid, and then you would confirm it with your wave number range. Now continuing on with your carboxylic acid, in addition to your OH group, you also have that carbon double bonded to your oxygen peak. So to your left here is typically your band region, and over here is typically your fingerprint region. So if you were to look at this next peak, this next very intense peak here, and this is labeled as your 1680 to your 1750, if you were to check your table of information, that wave number range will match your carbon double bonded to your oxygen, which are present in your aldehydes, your esters, your carboxylic acids, your ketones. So the presence of both this broad OH group and this carbon double bond to oxygen peak lets you know that this spectrum belongs to a carboxylic acid. Your fingerprint region over here would give you further information about what type of carboxylic acid it actually is. Your aldehydes and your ketone, in this case it's your acetaldehyde and your acetone, would have spectrums with peak in the similar region. So they're both going to have that carbon double bonded to your oxygen peak. So that's around your 1700-ish area. So this represents your carbon double bond to oxygen in your acetone, and this represents your carbon double bonded to oxygen in your aldehyde. It is important to note that your carbon to oxygen double bond within your aldehydes occur at higher frequency or more intensity than the ones in your ketones. Additionally, in your aldehydes, you're also going to have a weak to medium intensity peak of your carbon to hydrogen stretching band, which is typically in your late 2000 wave number region, so between your 2700 to about your 2800 and some change, right, that you won't have in your ketone. So now that we recap some of the basic, we're gonna look at the question that I did in class. So the question reads, the IR spectra in figure 2, 3, and 4 belong to compounds 2-propanol, an alcohol, butanoic acid, a carboxylic acid, and acetone, your ketone. Identify each of the compounds A, B, and C in figures 2, 3, and 4 respectively from the IR spectra provided. Justify your choice by indicating which band on the spectra was used to verify the identity of the compounds and indicate the functional group responsible for the band in each case. The question tells you that we have 3 options. We have your alcohol. I'm trying to squeeze it in here at the side. We have your acid, your carboxylic acid. And lastly, we have that ketone and the lack of space, okay? So in each of the cases, we're looking for a particular functional group. In our alcohols, we're looking for that OH group. For our carboxylic acids, we're looking for OH group as well, but a very broad OH group. And we're also looking for your carbon double bonded to your oxygen. And lastly, in your ketone, we're looking for that carbon double bonded to your oxygen. So from our previous recap, we should hopefully remember that when it comes to your OH group, you have an intense peak in both your alcohol and your carboxylic acid. Your alcohol is going to give you an intense OH dip on your spectrum, and your carboxylic acid is going to give you a very broad OH peak. So if I were to just visually look at your figures 2, 3, and 4, I would be leading towards figure 4 being your carboxylic acid because it's very broad OH group region here. And there's another peak that looks like a carbonyl functional group, but I won't say for sure yet until I match the wave number. At the bottom here, just going visually, I would say this can potentially be the alcohol because look at that look at that OH band or the OH peak on your spectrum. And by the method of elimination, I would say figure 2 is most likely your ketone. But now we're going to work through it. So we're going to start off with compound C that I was leading towards being your carboxylic acid. So I already see this very broad peak here, and typically this very broad peak leads to your OH functional group within your carboxylic acids. And this piece over here is typically your carbon to hydrogen band. So utilizing this very broad peak here, I would then determine the wave number of that peak. Because apparently my video was just not recording. So we're back here with your very broad OH group. If you were to very broad OH group, we draw down the line to then determine your wave number of this band or of this peak. And based on your data sheet, you would have determined that that wave number falls within the range of your OH group within your acids. We're already leading to because of the very broad peak on your spectrum. So the wave number from here I would have gotten between 3200 to 3300. So a number along that range, and it falls within your OH group range on your datasheet. So I've written the number along with your centimeters, bro. So I would have written the wave number, Cm minus, and then I would have given the OH functional group with that respective number as part of my justification. Our next intense peak on this spectrum is this peak right here. The tip is very, very narrow, so we can just draw down the line right there, and it lands directly on your 1700 mark. So if I were to go back to our data sheet and look for the range of that 1700, and also knowing that our carboxylic acid contains a carbon double bond to oxygen and your OH group, we can see that your carbon double bond to oxygen has a range of 1680 to 1750. And our determined wave number here lets us know that this is your carbon double bonded to your oxygen. So the presence of both your alcohol functional group and your carbon double bond to your oxygen is an indication that this spectrum is our carboxylic acid, which we're already leaning to based on the visual peaks. Our next spectrum that we're already leading to was your figure 3, which we are leading towards it being an alcohol because of this peak region right here. We have this lovely peak for the alcohol right here, and if we were to draw it down to determine its wave number, we would get around 1, 2, 3. We get around a 3350 for that wave number. And see that on your data sheet at 3350 actually falls in the range of your OH hydrogen bond in your alcohols, right on the money. So we can say, we will then use this in justification that this alcohol, that this OH group here, lets us know that the spectrum is for your alcohol. You will also see the presence of your carbon to hydrogen peak that is present here, but that doesn't let us know that this is an alcohol. The presence of that OH bonding within your alcohol lets us know it's an alcohol. So lastly, we have your figure 2, and that was determined based on your elimination of your other two options. So that left us with our ketone. From your module 1 IUPAC, you would remember, hopefully, that your ketone is your carbon double bond to oxygen as attached to two other R groups. Okay. So in your ketone, we now have that carbon double bonded to your oxygen presence that we're going to be looking for. So on our IR spectra for your ketone, you're gonna see some different intense peak. This is mainly in your fingerprint region here, and then in your band region you have a few weak peaks. For looking for your carbon double bonded to your oxygen group to justify this as your ketone, that's around your 1680 to your 1750. So 1500, 1600, 1700. So we're gonna be focusing in on this peak right here. And if we were to kind of draw it down at the bottom, it would be 17 and some change. right? And that change could be roughly 1710, 1715. So that would be our justification. Okay. So your other question from your sheet is a practice question, and I will go through the answer in our next class.